Hey, welcome back to the review for the final exam, College Algebra. We're at question number 21, going to question number 30. Let's get started. Given the polynomial function has the given 0, find the other zeros. And so one thing I'd like to start off with, since the degree is 3, how do you spell degree? Since the degree is 3, that means we're going to have 3 zeros. So if they give me a 0, that means that I need to find 2 more zeros. Another thing that I know is if 3 is a 0, then if I do synthetic division with that number, I'll get a remainder of 0. So let's do synthetic division. And that's going to knock this function from a cubic down to a quadratic. And then we can sing the song. All right, here we go. The 1 comes down. 3 times 1 is 3. 3 minus 5, negative 2. Times 3, negative 6. 11 minus 6 is 5. Times 3 is 15. Look at that. Remainder of 0. I knew it. If 3 was a 0, if I do synthetic division, I get a 0 remainder. Now, guess what that also tells me? Remember I said since the original function was cubic x to the third, that means that the quotient, the 1, negative 2, and 5, that's going to be a, b, and c, because this is now quadratic. And now I can sing the song. Here we go. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And then I can use my handy-dandy calculator to calculate the radicand. 4 minus 4 times 1 times 5. That's going to be a negative 16 under the radical. 2 plus or minus negative 16 under the radical. And I know the square root of 16 is 4. So that's going to be 2 plus or minus 4. Now check it out. Since the 16 is negative, that means the solutions are complex. Negative under the square root gives me an I in the answer. And then I can reduce. Now don't forget that this 2 in the bottom has to divide into both terms in the numerator. 2 divided by 2 is 1. 4 divided by 2 is 2. And so those are my other zeros. Those zeros are complex, and just for fun, that means that those are not x-intercepts, since they're complex. There you go. Those are the other two zeros. What, you don't see them? Okay, it's 1 plus 2i and 1 minus 2i. 1, 2. Those are the other two zeros in standard form, okay? But I'll accept the plus or minus answer. Next problem, write the vertical and horizontal asymptotes, list the x and y intercepts, domain, and graph. And we have a rational function this time. So, easiest thing to find first, rational function is the vertical asymptote. You simply take the denominator and you set that equal to 0 and solve. And for some reason, I can't write very good. Equal to 0. There we go. Moving the 5 over. X is negative 5. Vertical asymptote. Let's go ahead and lay that down over here, okay, on our graph. At negative 5. Vertical asymptote. Next, horizontal asymptote. Since the degree of the top is 1 and the degree of the bottom is 1, did you see that? The degree is the biggest power on any variable. So the degree of the top is 1. That comes from the power of x. The degree of the bottom is 1. That comes from the power of x. And when those degrees are the same, that says that y equals a over b is going to be your horizontal asymptote, where a is the coefficient of the numerator and b is the coefficient of the denominator. So that's going to be y equals 1 over 1, which is 1. And so there's our horizontal asymptote. And let's go ahead and lay that down on the graph. Going across. Bam! Vertical and horizontal asymptotes are done. Next easiest thing is the domain. And then how did they want it? They wanted the domain in set notation, which is nice because we know that the vertical asymptote and the domain, they correspond. So in set notation, that's going to be the set of all x such that x cannot be -5. Whoops. Brace. Got to have a brace. Now, why is it that? It's because if you go back to the function and look at the denominator, if x is -5, if I plug that in, -5 plus 5 makes the denominator 0. But the denominator can never be 0, so that means that x can never be -5. It can be anything else, just not -5, okay? And did you hear me say that the vertical asymptote and the domain, they correspond with each other, okay? So whatever the vertical asymptote is, that's the number that x can't be. Okay, what next? How about x-intercept? Let's find x-intercept next, okay? So to find an x-intercept, we want to let y be 0. And that's going to give me x minus 4 over x plus 5. But if I multiply both sides by the denominator, x plus 5 on both sides, 0 times anything is 0. Okay, so that's just going to give me 0 equals x minus 4. And if I move the minus 4 over, that says x is 4. And so that's going to give me an x-intercept of 4, 0. Okay, next, if I want the y-intercept, I need to let every x be 0. In other words, I need to calculate f of 0. And so that's going to be 0 minus 4 over 0 plus 5. And that's going to be -4/5, which is my y-intercept. 0, -4/5. And what else do they... Let's read the instructions one more time, okay? We've got the vertical and horizontal asymptotes. We've got the x and y intercepts as ordered pairs. We've got the domain in set notation. Okay, the only thing I need to do is graph. All right, so the x-intercept is at 4. The y-intercept is at -4/5. That's about there. And remember, the graph has to approach the asymptotes. And so that says that this graph is going to do something like this. It's going to come up like so. Coming through the x and y intercepts. And then on the other side, it's probably going to be up in this top portion, but the only way to make sure of that is to do an ordered pair. And I want to pick a number that is to the left of the vertical asymptote. I don't know, how about -9 just for fun? Just to pick a random way negative number over there. And to figure that out, we're going to plug that into the function, okay? -9 minus 4. -9 plus 5, what is that going to be? That's going to be -13/4, which is approximately 4 9 is 13. -13 over negative 4. And that is 3.25. Positive 3.25. Okay, it's not approximate. It is, I'm sorry, it's exact. It's not approximate. It's exactly 3.25. So let's see here. 123.25 is going to be about there. And so that shows me that this curve is going to do something like this. And so there's the answer, or I should say answers, all of the answers for question number 22 with all of the work shown. And that's it for page 8. Page 9. Solve and graph the absolute value inequality. We're going to write the solution set using interval notation. Oh, and it does say solve and graph. So there's like 3 things going on here. All right, so the first thing we need to make sure of is that the absolute value is isolated. Here we have only absolute value stuff on one side. And then if this is true, we're going to split it in 2. So is there positive stuff greater than or equal to 3? Yes, definitely that is true. So then this splits in 2. We're going to have 9x minus 2 greater than or equal to 3. And then the other time that it splits, it's going to be 9x minus 2, watch this, less than or equal to negative 3. Did you see that? What happens the second time it splits? You have to change the inequality and the sign. And the last thing we need to do is fill in the middle with the appropriate word. So if the original problem has a greater than, this is going to be or. If the original inequality was less than, the word in the middle is and. And that makes a difference when it comes down to the shading. All right, so now let's solve each one of these for x. Let's see, 9x greater than or equal to, that's going to become a 5. Divide both sides by 9. X is greater than or equal to 5/9. Or, moving the minus 2, 9x is less than or equal to, that's going to be minus 1. Divide both sides by 9. X is less than or equal to negative 1/9. Okay, now to the number line. Now to the graph. We have 2 critical points. They need to be in the right order. So that's negative 1/9 and positive 5/9. Are those going to be open or solid? They're going to be solid dots. And the last thing I need to do is I need to decide where to shade. And that's based on the inequality. So look back what it said. It said x is greater than or equal to 5/9, which means shading to the right of 5/9. X is less than or equal to negative 1/9. That means we're going to shade to the left of negative 1/9. And now that I have the shading completed, I can now write the interval notation. Notice that this shading goes to the left forever. So the shading's going to start at negative infinity, and it's going to end at negative 1/9 with a bracket because the dot is solid. And then we're going to have a union symbol because the U is the glue that sticks the 2 pieces together. So then we're going to pick back up at 5/9, and the shading continues forever to infinity and beyond. And so there is the solution set in interval notation, and there is a complete shot of that problem. Next, 24. Solve and graph the polynomial inequality. Again, we want to write the solution set using interval notation. And notice it does say solve and graph. So again, we got like 3 things going on here. It would be really nice if this trinomial factored. And so we're going to check and see if it factors. We're going to read the signs. Minus at the back makes them different. X and X. Are there numbers that multiply to make 18 and subtract to make 3? 6 times 3. And notice the 6 has to go with the minus because we need negative 3. 3 minus 6, negative 3. And then I can set each factor equal to 0 and solve. And those are not going to be the solutions. Those are going to be the critical points. So x equal negative 3 and x equals 6. Those are critical points. Okay, now to the number line. I've got my 2 critical points, negative 3 and 6. Are those open or solid? Uh-oh, they're open circles this time because the inequality does not have the equal to part. It's strictly less than. Now, to figure out the sections of shading, we're going to have to use test points. So we're going to need to come in here and pick 3 points that are in each section, okay? So I need a test point for this first section. It has to be a number less than negative 3. I don't know, how about negative 4? Next, we need a number that's between negative 3 and 6. How about 0? And then a number bigger than 6, 7, 8, 9, 10, whatever you want, okay? I'm going with 7. Now, the best place to plug those test points back into is the factored form of the inequality. And we're going to have to plug those in and test them to see if we get true or false, okay? Starting with negative 4. Let's see here. That's going to be negative 4 plus 3. Negative 4 minus 6. Less than 0. We want to know, is that less than 0, true or false? Well, that's going to be negative 1 times negative 10. But a negative times a negative makes a positive number. And a positive number is not less than 0. That is false. And then I know a little secret about these inequalities. I know that normally they alternate. So if the first section is false, then it's probably going to be true-false because they usually alternate, okay? But just to check and make sure, we're going to test the test points. So 0 plugs in for each x. We're going to get 0 plus 3, which is 3. 0 minus 6, negative 6. Negative times a positive makes a negative. And a negative is less than 0. That is true. And check this out. We're going to shade that section. Do you see we shade between the critical points because that section is true? And then we're going to test 7. 7 plus 3. 7 minus 6, less than 0. 10 times 1 is 10. That is not less than 0. That is false. And so now that we know the sections that are shaded, we can now write the interval notation. And this is going to be everything from negative 3 to 6 with parentheses, okay? So the final answer, negative 3 to 6. We're using parentheses because the circles were open circles. And that is the interval notation. And let's see, there. Is that it? There's a shot of number 24 full screen right there. And number 25. One more inequality. Write the solution set using interval notation. Again, it says solve and graph. And so what you need to know about a rational inequality, first of all, one side needs to be 0, which it is. If it wasn't 0, you would need to move that number over, or whatever is over there, move it over and make one side 0. But ours is 0. So what we're ready to do is take the numerator and the denominator, and we're going to set those both equal to 0 and solve, okay? And I just realized it would probably be better if they were like this. All right, so here we go. Moving the 1 over, 2x equals 1. Divide both sides by 2. X is a half. That is a critical point. For the other factor, for the other critical point from the denominator, moving the 4 over is going to give me x is -4. And those are my two critical points. Now I need to go to the number line with my critical points. -4.5. And then I need to figure out if those are open circles or solid dots. Okay, so listen closely. The numerator critical point is going to be either open or solid, depending on the inequality. So our inequality has the equal to part, so the 1/2 is going to be a solid dot. The critical point that came from the denominator can never be solid. Never. If it comes from the denominator, it has to be an open circle. And the reason is because if we let that be a solid dot, that means that I should be able to plug this in and get an answer. But the denominator would become 0, and that gives us an undefined situation. And so that's why the denominator can never be a solid dot. Next step. To figure out which sections are shaded, we're going to need to pick test points. So I need a test point less than -4. Let's go let's go big this time. -10. How about a number between -4 and +1/2? I'm going with 0. 0's always easy if it can be a critical, not a critical point, if it can be a test point. And then a number bigger than half, I'm going to go way big. Let's go 10 again, okay? Going with 10 again. Do you see it doesn't matter what you pick for test points, but you do have to use them to figure out which section is shaded. And the test points do have to actually be in the region you pick them in. All right, so now to test those test points. Let's see, plugging back into the fraction, we're going to get 2 times -10 minus 1 over -10 plus 4. We want to know, is that greater than or equal to 0? Well, let's see. That's going to be -21 over -6. Negative over a negative makes a positive, and that will be true. And remember, that means that we want to shade that region if it's true. And that also means that this is probably going to go false true. Probably. You do need to actually work it out and check just to make sure. But 95, 98% of the time, those are going to alternate. Okay, checking the 0. 2 times 0 minus 1. 0 plus 4. Is that greater than or equal to 0? Let's see. That's going to end up being -1/4. Negative numbers are not greater than or equal to 0. That's false. And then last, we're going to check 10. 2 times 10 minus 1. 10 plus 4 greater than or equal to 0. That's going to be 20 minus 1 is 19 over 14, which is definitely greater than or equal to 0. That is true. And so now that I have verified the shaded regions, now I can write the interval notation. And I'm all but out of room. Let's see if we can squeeze it in right here, okay? So the shading begins at -infinity, and goes to -4, and that's going to get a parenthesis, union, this is not going to fit. I'll have to find out somewhere else to write this. What can I sacrifice? Where can I put this? I don't know. Let's see if I can fit it right up here. We'll erase these. All right, so what did we say? We said this was true, false, true. We'll put those down there. Now then, minus infinity to -4. Don't forget the u. Remember, the u is the glue that sticks the two pieces together. And then don't forget, again, we're using a bracket because at 1/2 the dot is solid to infinity. And there is our interval notation solution right there. And there's number 25 all in one screen. Next, number 26, a one-to-one function is given. Write an equation for the inverse function. And this is going to be the 3S method. Anytime you're finding an inverse function, you want to use the 3 S's. And the 3 S's are substitute, switch, and solve. So the first S, substitute, says that we're going to replace f of x with y. That's the first S. Substitute for f of x, replace it with y. And the second S is switch. We're going to switch x and y. And then the third and final S is solve. We're going to solve for y. And so the first thing I'm going to need to do to solve for y is I'm going to need to get rid of this fraction. Okay, so let's see. Let's continue this up here. Now, to get rid of a fraction, all you got to do is multiply both sides by the denominator. And those will cancel. And then this x is going to need to distribute. So that's going to give me xy plus 9x equals 8. Don't forget we're solving for y. So the next step is to move the 9x over. That's going to give me xy equals 8 minus 9x. And the third and final step, divide both sides by x. Okay? Now that we have y by itself, we can write the inverse function using the inverse notation, which looks like f to the -1. That is the inverse function. And that is going to be 8 minus 9x all over x. That is one way you could write it, okay? Or, if you wanted to reduce this, an alternate answer could be 8 over x minus 9. Now, you don't have to have them both. One or the other would be fine. But I want you to notice that you cannot cancel these x's unless you separate into two separate fractions. The 8 has to be over the x also. And then if you do 9x over x, the x's will cancel and leave you 9. And so there's the two acceptable answers for number 26. Again, you don't have to have them both. One or the other is fine. Next page. Number 27, graph the function, showing the asymptote as a dashed line. Write the domain and range, interval notation. Oh, and we got to identify transformations. All right, let's do the transformations first, since they're freaking easy. +3, outside the function. Any number added or subtracted at the back of the function, that is a vertical shift. Plus is up, minus is down. So this is going to be an up shift, up 3, okay? Then notice we have a number that is added directly to x, and we're going to call that inside the function because it's part of the exponent here. This is an exponential function, and any number added or subtracted directly to the x inside the function, that is a horizontal shift. Plus is left, minus is right. So since it's a plus, it's going to go left. How far to the left? 3 units. And then now that we know the transformations, we should be able to graph the function, okay? So the basic function right here, 4 to the x, if I were to sketch a graph of that, if x is 0, y is 1, and if x is 1, it's 4. All right, so this is the parent function, f of x equals 4 to the x. This is what the exponential function looks like without the transformations. If I perform the transformations, let's consider this y-intercept here. That's going to shift up 3 and left 3, okay? So 1, 2, up 3, 1, 2, left 3. And so that point is going to transfer to there. 1, 1, 2, 3. That point's going to transfer to there because this was over 1, 1, 2, up 3. So over 1, up 3. And then we're going to have an asymptote across here. So let's get rid of the parent function. And what else did it want to know? Did it want the it did say, right? The asymptote as a dashed line. And just so you know that this vertical shift, the plus 3, that is going to be your horizontal asymptote. That's how you can find your horizontal asymptote. Bam, 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 bam. So at plus 3, we're going to have a horizontal asymptote. And our function is going to do something like this. And if you weren't 100% sure with the transformations and you wanted to check and make absolutely sure that you were right, you could make a table of values where you pick numbers like -3, maybe -2, -3, -4, and you can plug those in and see what you get, okay? So just to do those real quick, -3 plus 3 is 0. That's 1 and 3 is 4. So at -1, 2, 3, I should be up at, let's see. At -3, I should be up at 4. 1, 2, 3, 1, 2, 3, 4. And I am. At -3, I'm at 4. At -4, I would be at 3.25. And you can use a calculator if you want to check that. And then at -4, I'm sorry, at negative, that's not right. At -4, I'm at 3.25. And at -2, let's see, plugging that in, -2 plus 3 is 1. 4 to the 1 is 4. 4 plus 3 is 7. I'll be at 7. And that verifies this point right here. So if you needed to use a table, you can, although it's not mentioned in the instructions. In fact, I think in the instructions it says, no, it doesn't say use transformations. It just says graph the function, okay? So you can either graph it with transformations or you can graph it with ordered pairs, but you do need to show this horizontal asymptote as a dotted line. And at this point, we should be able to finish this with the domain and range, okay? So the domain is all real numbers. And we know that because the graph goes to the left forever and it's going to go to the right forever. There's no restriction on x. However, the range does have a restriction. The graph is never going to go below 3. In fact, it's never going to even get to be 3. And so notice if we go from bottom to top, this graph is going to start at 3 and go up forever. So we definitely don't want to use a bracket. We want to use a parenthesis on the 3 because there's an asymptote and it'll never touch at 3. And let's see, did we get everything for number 27 done? We got the graph, asymptote, we got the domain and range, and we identified the transformations. Yay, that's all done. Number 28. We have a money problem. And here's what I want you to notice. It says compound quarterly. That means we're going to be using the compound interest formula, which is A equals P, 1 plus R over N to the NT. And all you have to do is plug and play. So the principal is 12,000. 1 plus, the rate is 6%. Now that is 0.06 as a decimal. The N is the number of compounds, and it says compound quarterly, so that makes N 4. If it would have said something like compound semi-annually, N would be 2. Or compound monthly, N would be 12. And so the word that they use there, compound whatever, that's important. Notice there's an N in the exponent, so that's going to be 4 times T, and T is also 4 years. And then we need to plug this into our handy-dandy calculator and round to the nearest penny. 12,000, 1 plus 0.06 divided by 4 to the 16. 4 times 4 is 16. And that's going to be 15,227 and 83, if we round it, 83 cents. Okay, and I feel like I wrote that terribly. Let me erase those and finish that out again. $15,227 and 83 cents. And again, now that 15 looks too big. Just like so. Bam. 28 is done. That's the end of page 10. Next, 20. Oh, it's another graph. This time it's a log function. So what do we know about log functions? We know that the x minus 5, if we set it equal to 0 and solve, is going to give us our vertical asymptote. So x equal 5 is the vertical asymptote. So let's go ahead and lay that down. Bam. Y'all see? Do I need to zoom in? Do you see that? Vertical asymptote at 5. And let's see here. Let's make a little table of values. And I have a feeling that x is going to have to be bigger than 5. So let's say, what's a number bigger than 5? 6, maybe? And then we're going to use our calculator to calculate the values. So with the Casio FX115 ES Plus, it's real easy to do log base 6 of 6 minus 5, which is 1. In fact, you don't even need a calculator for that. Log of 1 is 0. No matter what the base is, log of 1 is 0. And that gives me the x-intercept. And then let's do... I'm going to pick 11. Is 11 even on here? I'm going to make it work, okay? Now, why would I want to do that? You're going to see in just a second why I would want to pick maybe 11. If I plug 11 in for x, what is 11 minus 5? What is 11 minus 5? That is 6. And if I do log base 6 of 6, that's going to come out a nice whole number of 1. So if this is minus 10, this is going to be like something like here. And then if I do one more x, I'm going to do something like 5.5. I think 5.5 may give us a decent number. Let's see. Log base 6 of 5.5 is 0.95? Log base 6 of 5.5. Log base 6 of 5.5. 0.95. Let me try a different. Something doesn't feel right. Log base 6, about 5.1. Log base 6 of 5.1. Nope, I'm missing something. That's 0.9. Oh, duh. I'm not doing the minus 5. Good grief. So if I do 5.5 and I plug it in, what is 5.5 minus 5? That's 0.5. I really should be doing log base 6 of 0.5. Okay, negative 0.4. Is what that is. And so what does that say? That says that this is going to curve down as I get closer and closer and closer to the asymptote. And then real quick, it's going to curve up to the right, like so. Something like that is the graph. And we never did identify the transformations. Let's go back and do that real quick. All right, so there was no number outside the function. So that means no vertical shift, up or down. I'm just going to put none because there was no vertical shift, but there was a number inside the function. Remember the number that's added or subtracted directly to x? That is your horizontal shift. Plus is left, minus is right. And so we're going to have a shift to the right 5 units. Now, can you see that the vertical asymptote of a standard log function, if we go back and look at this, of the parent function, the vertical asymptote would have been at the y-axis. That has been shifted over 5 to the right. So this does represent a shift of 5 to the right, and that helps me feel like I'm right. No pun intended. And then we can do the domain and range. Now, moving from left to right, we can see that this graph is going to begin at 5, but it cannot be 5 because there's an asymptote. So we're going to use a parenthesis, which says 5 is not included, but it will go to infinity. The range goes from bottom to top, and it is going to be minus infinity to infinity, because this graph is going to go down forever, and as it goes to the right, it is going to continue to creep up forever. It's going to continue to increase forever. And so that should do it for question number 29. We've got the graph, make sure, graph. We've got the asymptote, domain and range. We identify the transformations. Bam. All right, number 30. And this is going to be the last problem for this video right here. Express as a single logarithm. Using the properties of logarithms as a single logarithm, that means we're going to be condensing. That means condense. Condense. That N looks like a U. And that means that the coefficients have to go first. So the power rule says that if you have a coefficient of a log, that coefficient can come up and become the power. So we're going to use the power rule first. The 4 out front becomes the exponent of t to the 4th. The other log does not have a coefficient, so we're just going to bring him down. And now that the logs do not have coefficients, now we can notice subtraction is going to turn into a fraction. That's the quotient rule. So the two logs become 1. The t to the 4th is on top, and the s goes on bottom. Did you catch that? The quotient rule says subtraction turns into a fraction, and whoever comes first is on top, okay? And the second guy goes on the bottom, and that is done. If you have any questions or comments, feel free to put them in the comment section below, or you can text me. And thanks for watching.